So in today's video, we'll be discussing about mechanics, that is the paper 4 of 9709 mathematics. So we will discuss all the topics, that is force and equilibrium, kinematics of motion in straight line, momentum, then Newton's law of motion, and energy, work and power. So it would be a detailed video and I will discuss all the topics in a detailed way, and after watching this video, you can start solving topical and yearly past papers, and I would give the link of the PDF in the description. There is the link of the PDF. So in today's video, we'll be discussing about mechanics, and mechanics is paper 4. It is a 50-mark paper and there is usually 6 to 8 questions. On an average, there is 7 questions, and it is a 1 hour 15-minute paper, and it is an easy paper. So force. So force, its SI unit is Newton, and it is a vector quantity. That means it contains magnitude and direction. Then resultant force is equal to forward force minus backward force, and resultant force is equal to mass into acceleration, or force is equal to mass into acceleration. Then for a right angle triangle, the side that is adjacent to the angle is adjacent, the side that is opposite to the angle is opposite, and the longest side is hypotenuse. So sin theta is equal to opposite by hypotenuse, sin theta is equal to opposite by hypotenuse, cos theta is equal to adjacent by hypotenuse, and tan theta is equal to opposite by adjacent. Then for an inclined plane, let's suppose this is our object, and for this object the weight is acting vertically downwards. So the weight is acting vertically downward, and we know that weight is equal to mass into gravitational field strength. So mass into gravitational field strength is acting vertically downward, and for this weight, that is mass into gravitational field strength, we need to find the horizontal and the vertical component of the weight. So the horizontal and the vertical component of the weight with respective to this plane. So with respective to this plane, we need to find the horizontal component and the vertical component with respective to this plane. So the horizontal component is mg sin theta, that is the horizontal component, and the vertical component is mg cos theta, that is the side adjacent to the angle is cos and the side that is opposite to the angle is sine. Or you can find these sides by using, let's suppose this side is x, then theta. So in this right angle triangle, we consider the angle theta, the side x, and the hypotenuse, that is mg. So theta is equal to opposite by hypotenuse, so sine theta is equal to opposite, that is x, and the hypotenuse is mg. So what is x? X is equal to mg sine theta. So this side is mg sine theta, and the direction of this force is like this. That is, since the weight is a resultant force, so for this resultant force, this forms a triangle, and this is not a closed triangle, and you have to remember that for a closed triangle, the resultant force is 0. But since it is not a closed triangle, there is a resultant force, that is the weight, so the force forms the weight. And this side is mg sin theta. Similar to this working, we can find this side as mg cos theta, that is, if we consider this side as x, then cos theta is equal to adjacent by hypotenuse. So the adjacent side is this side, and we consider this side as x, by hypotenuse is mg. So x is mg cos theta. So here we find this side as, or the vertical component of the weight, as mg cos theta, where this angle is theta, so this angle is similar to this angle. For friction, so friction is the opposing force. Let's suppose the object is moving in this direction, then the friction is acting opposite to the direction of motion. That means since the object is moving in this direction, so the friction is acting in opposite direction. And friction is calculated by the formula friction is equal to mu r, where mu is the coefficient of friction and r is the normal reaction force. And what is normal reaction force? Let's suppose this is the object and this is the normal reaction force by the surface, so this is r. And let's suppose this is the surface, then the normal reaction is force is exerted by the surface and is perpendicular to the object. That is, this is the normal reaction force, and this force is acting like this. So this is the normal reaction force. Similarly, this is the normal reaction force. So friction is equal to mu r. For a smooth surface, let's suppose this surface is a smooth surface, then there is no friction that is acting. But if let's suppose the surface is not a smooth surface, or let's suppose the surface is a rough surface, then friction is acting, and friction is calculated by the formula friction is equal to mu r. And most of the time you have given the value of mu. So tension, let's suppose this is our object, and this object is pulled by a string. So this is the string. So the tension force is acting away from the point of observation. Let's suppose this is the string and this is the object. So tension force is acting away from the point of observation. If let's suppose we consider the object as the point of observation, then the tension force is acting away from the object like this. And let's suppose for this object, this is the string. And what is the direction of the tension force by the string? So tension force acts away from the point of observation. And if we consider this object as the point of observation, then tension force is acting away from the object. So tension E, then resultant force is calculated by the formula F is equal to ma, and frictional force is F is equal to mu r. Then let's suppose this is just a surface or a floor, and this is the string, and this is a ring. So, and this is our object. So if a ring is placed, then let's suppose the string is like this, or initially the string is like this. And if an ring is placed and then an object is placed, then the ring would balance until the string becomes equal in length. So the ring balances the length of the string until both the lengths are equal, and the force, that is a tension force on each side of the string, is equal. So when a ring is placed, the tension on both sides of the string are equal. For example, as we can see that there is a ring, so the tension force on each of the string is equal. And what is the tension force? Tension force is acting away from the point of observation. So if we consider this object as the point of observation, the tension force is acting away from the object. So tension force is acting away from the object, and since the ring is placed, so the tension force is same on both sides of the string. Now here we can see that this is a so here basically the two objects are connected by a string or a rope. And what is the direction of the tension force? Tension force is acting away from the point of observation. So if we consider this object as the point of observation, tension force is acting away from the object. Similarly, if we consider this object as the point of observation, then tension force is acting away from the object. Tension. So this is the same diagram as given. Then for an object at limiting equilibrium, so limiting equilibrium means the object is about to move, or the body is about to move. Let's suppose this is our car and it is moving. And for a car that is in limiting equilibrium, that means it is pulled. Since the car is pulled by a tension force and the car is in limiting equilibrium, that means the car is about to move. It is at stationary, but it is about to move. It is stationary, but about to move. So if the car is at limiting equilibrium, then the car is stationary, but it is about to move. So at equilibrium, the body is about to move. Then for limiting equilibrium, the body is about to move. And since, let's suppose this is the object and it is about to move. Since it is about, so about to move. And since it is about to move, then friction is acting, that is mu r. So frictional force is mu r, and let's suppose if the object is at rest. So at rest, no friction is acting. Since the object is at rest, so no friction, or so at rest, since it is not moving, so we don't need to, or there is no friction. So at rest, there is no friction. At rest, no friction. But if let's suppose the object is moving, then we have to mention friction. And if let's suppose the object is moving in this direction, then the friction is acting in opposite direction. And let's suppose the object is about to move. Since the object is about to move, that means still friction is acting. So the object is not moving, but it is about to move. Still friction is acting, and friction is equal to mu r. So since the object is about to move in the forward direction, so the friction is acting in the backward direction, that is mu r. But since the object is not moving, it is about to move, so friction is acting. But at rest, no friction is acting. So equilibrium means that for an equilibrium, we can draw a closed triangle to ensure that it is an equilibrium. That means here we can see that the resultant force is zero, so the object is at equilibrium. And at equilibrium, the sum of the forces is zero. That means the force on the right is equal to the force on the left, and the force up is equal to force down. That means at equilibrium, the object is at rest. So the object is at rest, or the object is moving at a constant speed. So at equilibrium, the object is at rest, or the object is moving at a constant speed where there is no acceleration. Kinematics. So for distance and displacement, let's suppose this is the distance traveled by the object, this is the starting point, and this is the ending point. So the overall distance traveled is this distance. Now what is the displacement? Displacement is from the starting point to the ending point. So from starting point to ending point, and the displacement is a straight line. So this is a straight line from the starting point to the ending point. So the displacement is a straight line from the starting point to the ending point. So this is the distance traveled, and this is the displacement. So displacement is the straight line from the starting point to the ending point. Now speed and velocity. So speed is equal to distance by time, and velocity is equal to displacement by time. And speed and velocity has a unit of meter per second. And for acceleration, acceleration is equal to change in velocity by change in time. Then distance and speed, they are a scalar quantity. That means they have magnitude only. While displacement and velocity are vector quantity. That means they have both magnitude and direction. So displacement, velocity, and acceleration are vector quantity. Then acceleration is equal to change in velocity by change in time, and its unit is meter per second square. So for gravitational field strength, let's suppose this is the object in air. So the weight is acting vertically downward, and weight is equal to mass into gravitational field strength, and this gravitational field strength is g. And for gravitational field strength in mechanics, it is 10 meter per second square, and for physics you have to consider 9.81 meter per second square. And you have given these values in the data booklet or in front of the question paper. Then for constant speed, let's suppose the object is moving at a constant speed. At constant speed, resultant force is zero. That means forward force is equal to backward force. So forward force is equal to backward force, and at resultant force is zero. So resultant force is equal to mass into acceleration. So at constant speed, since resultant force is zero, and we know that resultant force is equal to mass into acceleration. So since the resultant force is zero at constant speed, so the acceleration would also be zero. Then we need to use these three formulas for motion or for kinematics. That is the equation of motion. So S is equal to ut plus half a d square, where S is the displacement, U is the initial speed, V is the final speed, and t is the time taken. So S is equal to ut plus half at square, v square minus u square is equal to 2s, v is equal to u plus at, and sometimes we need to use S is equal to vt minus half at square, but we don't use regularly. But you need to still know this formula, because sometimes when all these three are unworkable or we cannot use this formula, then we need to use this one. That is S is equal to vt minus half at square. So S is equal to ut plus half at square, v square minus u square is equal to 2s, v is equal to u plus at, and S is equal to vt minus half at square. And you have given all these formulas in the data booklet. A is the acceleration. Now for velocity, velocity is equal to displacement by time. So the area under the velocity time graph is displacement. So area under the velocity time graph is displacement, and the gradient of the velocity time graph is acceleration. So area under the velocity time graph is displacement, and the gradient of the velocity time graph, that is this gradient, is acceleration. Then for displacement time graph, so for displacement time graph, so here we can see that acceleration is equal to velocity by time, and also velocity is equal to displacement by time. So the gradient of the displacement time graph is velocity, and the gradient of velocity time graph is acceleration. Then for momentum, so momentum is always conserved. So you have to remember that momentum is always conserved. So that means since the momentum is always conserved, or the momentum stays the same, so total momentum before collision is equal to the total momentum after collision. And we know that momentum is equal to mass into velocity. So this is the momentum, that is the momentum, and it is mass and velocity. So momentum is equal to mass into velocity. Then for work, energy and power, so work done is equal to force into distance. So work done is equal to force and the distance moved in the direction of the force. For example, this is the object. So the force is acting in this direction. So the distance traveled by the object must be in this direction. That is the distance. So the work done is the force and the distance traveled in the direction of the force. Force and the distance traveled in the direction of the force. So the unit of work is joule. Then, so let's suppose the object is moving from this point to this point, and the force is acting in this direction. So we know that work done is the force, that is the force, and the distance traveled in the direction of the force. But since the force is acting in this direction, so we need to break the force into its horizontal and vertical component. That is, force is equal to, the adjacent side would be that F cos theta, since the angle is theta, and the opposite side of the force, that is the vertical component of the force, is F cos F sin theta. F sin theta. So for this force, we know that work done is equal to force and the distance traveled in the direction of the force. So the distance traveled is in this direction. So the first force must be in horizontal direction. That means we need to consider only the horizontal component of the force. So the work done would be horizontal component of the force, that is F cos theta, and the distance. And we don't need to consider the vertical component of force because the object is moving horizontally. So since the object is moving horizontally, so for work we need to only consider the horizontal component of force. And here we don't need to use the vertical component of force since there is no vertical movement on the vertical direction. Then for energy, so energy can be gravitational potential energy, kinetic energy. So gravitational potential energy is mgh, that is gravitational potential energy, that is ep or gpe, is equal to mass into gravitational field strength, that is gravitational field strength, and height. So the SI unit of energy is joule, or the unit of energy is joule. The unit of energy is joule. Then for power, power is equal to work done by time taken or energy by time taken. Power is equal to work by time or energy by time. Also, power is equal to force into velocity. That is, power is equal to force into velocity, and this force must be driving force. So velocity, power is equal to force into velocity, and the force must be driving force. That is driving force. So the SI unit of power is watt. Then by principle of conservation of energy, so you need to solve the most of the problems for energy by principle of conservation of energy. So by principle of conservation of energy, that means energy is always conserved. So energy before is equal to energy after. And what is the energy before? So the before, it can be gravitational potential energy, kinetic energy, and work done by driving force. So before, it can be gravitational potential energy, kinetic energy, or work done by driving force. And after, it is gravitational potential energy, kinetic energy, and work done by resistance, or work done against resistance. So that means initially, the object may have gravitational potential energy, and after it may have gravitational potential energy, and before it may have kinetic energy, after it may have kinetic energy, and for before we need to consider what done by driving force, and after we need to consider what done against resistance. We would solve these problems in our later videos, that is the solving of topicals and ELS papers. So this is the end. Thank you.